after some technical problems, we start this lecture. And today we continue our discussion of angular momentum. And here is application of this concept. So we defined angular momentum as vector product of radius vector r of a single particle times momentum of this particle. And this is the angular momentum of a single particle. If we have a solid body consisting of many particles, or if we have many particles, separate particles like planets in the solar system, then in order to find the angular momentum of a system of particles, we just have to find the vector sum of all angular momenta of each particle, various particles. So, if this usual vector, then it can be presented in the form of its coordinates. So there is a coordinate along the x-axis and the component of vector along the y-axis, and another component along the z-axis, where I, j, k are unit vectors directed along the unit vectors directed along the axis of three axes of Cartesian coordinate system, coordinate frame. So, what is the component of this vector? For example, what is this single component? How can we imagine it? How can we understand it? If this component is directed along the z-axis, then let's draw a picture showing this z-axis and some rotating body. So that if this body rotates, then the velocity of this point is directed along the tangent line to the circumference, to the trajectory, and it will be vector of its velocity. And also this point will have some radius vector r relative to some reference point O. So this is the reference point, and that's the radius vector r. And what does it mean if there is an angular momentum? It means that this point has some mass, and there is some momentum, mass times velocity, and vector product of r by momentum will give you the total vector L. This vector of angular momentum will have a z component, which is directed along the z-axis. And this z component can be calculated as the radius of rotation radius, capital R. Multiplied by momentum, actually multiplied by the vector velocity and mass of the particle. And if you find a vector product of this radius of rotation and velocity, you will rotate the screw in such a way that the screw will go upward. So we continue. And I repeat very briefly that we considered the vector of angular velocity and the components of this vector along the three Cartesian axes, and the z component, for example, as one of the components, can be depicted as the component directed along the z axis. And here is how to calculate this component if we have a solid body rotating with some point having velocity v and radius capital R of rotation. So, if there is a force acting on this point, the origin of this force may be anything. It may be a force of gravity, a force of electromagnetic interaction, electrostatic force, magnetic force acting on a moving charge, anything, or a force of acting from some spring attached to this point. So any kind of force applied to this point. How can we depict this force? Well, I will draw the force, for example, well, in order to be clear, I will choose a different point in order to not complicate things around this point where there are many lines already. I will take some arbitrary point and arbitrary force applied to this point. This force can be decomposed into three perpendicular directions. I will choose one direction along the radius vector. That will be the component of the force along the radius vector. Another component will be directed along the tangent line to the trajectory, and I will call it, as it a tangent component, I will use tau as the index here. And the third component will be a component directed along the z-axis, parallel to z-axis, fz. So the picture may not be quite convincing, but anyway, imagine three components perpendicular to each other. One component is along the z-axis, another component is along the radius, which is capital R, and another component tangential to the point trajectory. So three components of the force. And the force is this vector, which I try to imagine as consisting of three perpendicular components. Which component will be important of all these forces? Can component Fz change anything in the rotation of this body if the axis of rotation is fixed in some bearings? If the axis is fixed here, the axis is fixed, it cannot be changed in space. Can Fz component change anything in the rotation of this body? No, it can do nothing. Can the radial component Fr change anything in the rotation of this body? Again, no, nothing. Only the tangential component can either accelerate rotation or retard the rotation. Only tangential component. The other two components will have no effect on the rate of rotation of this body. So if we go to the equation of describing the change of angular momentum, rate of change in time, which we know is the vector of torque, the vector m called the torque, then as far as components are concerned, we will say that Lz component change in time, which is actually dLz dt, will equal that component of the torque which is due to tangential force, and that will be equal to radius of rotation, capital R, times tangential component of the force. No vector signs, so this is a scalar equation. This is a scalar equation. That's how it works. If we go deeper into the simple equation determining the rate of change of angular momentum, that's a vector equation, and vectors may be somehow directed in space. So in order to analyze this equation using the components of vectors, we have to take into account such simple equations for each component, actually for each component. I have demonstrated how it can be calculated for a z component of angular momentum, and only tangential component of the external force is useful to either to increase the rate of rotation or to decrease it. That is, only tangential force can change the Lz component of the angular momentum vector. That's the main thing which you have to understand. And now we go further, and we will try to apply the concept of angular momentum in mechanics of celestial bodies, in the motion of the planets in the solar system. So if we have planets moving in its, each planet moving in its own trajectory around the sun, you know there are 3 laws of Kepler, 3 Kepler's laws, which describe the motion of planets. We discussed these laws last semester, didn't we? Okay. So you remember the Kepler's laws. How did Kepler come to discover his laws? He used experimental data of the first European astronomer, who was Tycho Brahe. A Danish astronomer who was the first in Europe to use telescopes with precise measurement of planet coordinates on the sky. And Tycho Brahe spent many years of his life observing planets each day, and he registered coordinates of planets, each planet coordinates on the sky. And he entered this data in special table. He created a lot of tables with experimental data, with tables containing coordinates of each planet for each day of observations during many, many years. So that was a huge work, experimental work, every day, except those days when the sky was not clear, except those days when the sky was covered with clouds and planets could not be observed. So when the sky was clear, he used all this time
during many years, as far as I don't remember how many years, but at least 20 years of his life he spent on these observations. So he created huge tables of data, huge tables containing daily coordinates of each planet, digits, etc., etc., thousands of digits. And German scientist Johann Kepler was an assistant to Tycho Brahe. He was younger and he was his assistant. He was working with him. And while Tycho Brahe accumulated experimental data, the data of experimental astronomical observations, Johann Kepler helped him in some way, and then he started processing the data. He wanted to discover some laws which govern the experimental data, those thousands of numbers. And Johann Kepler processed thousands of numbers for each planet, and thus, while processing huge sets of experimental data, he discovered his laws. Such was the history. What were the laws of Kepler? You remember, the first law formulates something like that. Each planet moves along a trajectory around the sun, which is flat. First of all, the trajectory lies in a single flat. It's not a three-dimensional curve, it's a two-dimensional curve. That's the first fact. And also this trajectory in a flat is described by an elliptical curve, is an ellipse. Is an ellipse, I will try to show an ellipse, such that the sun is in one of the focal points of ellipse. There is another focal point where there is nothing. An ellipse has two focal points. For example, point C, which is empty, and point M, where there is the sun. And each planet moves along an elliptical orbit, elliptical trajectory, with the sun in one of its centers. What is the ellipse? What kind of curve is that? Ellipse is such a curve that for any point on this curve, the sum of distances to its focal points, say x and y, is the same. X plus y is constant for ellipse, for given ellipse. X plus y is constant. So the sum of distances to focal points is the same for each point. Whether I take this point or probably this one, there will be other distances, or this one, there will be other distances, or this one, there will be other distances, etc., etc. For this point, the distances will be this one. If we take the sum of these two distances, it will be the same for all the points. That's the definition of ellipse. And Kepler found that a planet trajectory fits into this rule very well. It means that the planet goes along an elliptical trajectory, with the sun being in one of its focal points, and the other focal point is empty. Before we go to the second Kepler's law, I will tell you a few things what happened next. Newton was aware, you know, I told you about it. Newton studied the works of Kepler, and he read that a planet moves along an elliptical trajectory. And Newton wanted to explain such a motion. He understood that such a motion cannot emerge from nothing. There should be some reason behind it, some cause, some forces which act on a planet and make the planet move along such trajectory. Newton understood that this trajectory is not the simplest thing in the world, but this is the consequence of some more simple things, some more fundamental facts. So Newton, when he analyzed Kepler's laws, he discovered his fourth Newton's law, that is a law of universal gravitation, and using his fourth Newton's law, a law of universal gravitation, he was able to explain the elliptical trajectories of planets. He was able to explain. You know what is the Newton's law of universal gravitation? How can we use it? We can take the mass of a planet and acceleration of the planet. Mass times acceleration is the force acting on the planet. And the force is universal gravitation constant, the mass of the planet, capital M is the mass of the sun, the central gravitating body, divided by distance squared. The distance from the planet, here is the planet M, and the distance R from the central body. And this can be written as minus gamma small m capital M divided by R squared, and here I will put it like vector R divided by the length of vector R. So this is the unit vector, vector R, this one, divided by the length of vector R. This is the unit vector, which can be denoted by E. And this unit vector looks in the direction away from the sun. But the force applied to the planet is directed towards the sun. So the direction of this force should be opposite the direction of the unit vector. Therefore, we have minus sign here, because this is a vector equation. This is the vector, and this is the vector. And in the middle, I wrote something scalar, which should be understood as an intermediary, as a preliminary result. This is not a exact equality. This is just a deliberation about what force should be. Actually, the force is not scalar here. The force is vector. So we should take the first term in this equality and the last term. And this can certainly be written as minus gamma small m capital M divided by R squared and unit vector E, which is directed along the radius. So Newton wrote such an equation. And this is a differential equation because velocity is the function of time and the radius vector, the distance from the planet to the sun, is also a function of time. So we have this function of time and this also function of time. It's possible to exclude time and imagine velocity as the function of radius vector, so that will be a differential equation with respect to radius vector. And we can find the velocity as a function of distance to the sun. This is a mathematical problem. This differential equation can be solved, and Newton did it. He successfully solved this equation. And from this equation, from his law of universal gravitation, Newton succeeded to prove that planets should move along elliptical trajectories. Newton proved it. He obtained the trajectory of the planet's motion around the Sun, Newton obtained this curve from his law of universal gravitation. But in order to do that, he had to develop the calculus. Just one little step. A huge science of calculus was developed by Newton in order to solve this problem of motion of celestial bodies. So the first Newton law, the first Kepler's law was obtained by Newton and derived by Newton from the Newton's law of universal gravitation. The first Kepler's law was explained by Newton. Well, as we had more than 5 minutes lost in the beginning, we will work without interval, okay? As far as the second Newton law is concerned, Kepler's law is concerned, I will consider it a little bit later. And now we will think about what other laws. Well, why not? Well, why not? Well, we can consider it right away. Sure. The second Kepler's law. What does it say? The second Kepler's law. I will put it here. So as far as the first Kepler's law, you know it. It says that the trajectory of each planet is a plane curve. It's not a three-dimensional curve. It's a two-dimensional curve, and it's an elliptic trajectory with the Sun being in one of the focal points of this ellipse. So that's the first Kepler's law. The second Kepler's law says something different. It says that if a planet is going along its trajectory about the Sun, along the elliptical curve, then in equal time intervals, the radius vector showing from the Sun to the planet will sweep equal areas. That is the area of this figure, the area A. It's not work, it's area. Is the function of time. And according to the second Kepler's law, this function of time is a linear function with some constant. It's not the velocity of light, it's just some constant, let it be something like alpha t. This area is proportional to time. So if you observe the planet motion within 1 minute, and then another minute, and then another, probably 1 hour, another hour, you will see that this radius vector sweeps larger and larger area. And this area, starting from the very first point of observation, this area covered by the radius vector is proportional to time. So that in equal time intervals, the area swept will be the same. Whether you measure it here or whether you measure it here, this area swept by the radius vector within 1 minute will be the same here and here on different sections of the planet's trajectory. The area will be the same. Because the area swept in a unit time is dA, dt, it's just alpha, the same, the constant area swept in each equal interval of time, equal time interval. That was an experimental fact derived from huge data obtained by Tycho Brahe, by Kepler. When he processed all these thousands of numbers, thousands of figures accumulated by Brahe, Kepler derived this law. So the first Kepler's law describes just the trajectory of the planet and says nothing about the speed of motion, while the second Kepler's law speaks about the speed of planet's motion. It says that when the planet is closer to the Sun, its velocity is larger. The planet's velocity is larger than if compared to the time intervals when the planet is farther from the Sun. So here the velocity of the planet is smaller, and here the velocity of the planet is larger. So that the area swept by the radius vector is the same if we measure this area during the same time interval. For example, during 1 hour. The area swept here during 1 hour and the area swept here, the area will be the same. So in order to derive this second Kepler's law, and Newton did it, Newton derived it, he obtained it, he explained it, we must use the law of conservation of momentum, the law of conservation of angular momentum. If we take the angular momentum vector, which is equal r times mv, then we know the law of conservation of angular momentum, which says that this quantity, both vector and its magnitude, remain constant in time if there are no external forces acting on the system. And when we observe the solar system and the planets, no external forces actually are important, because all the stars, other stars, are very far away and their action is very small and negligible during the time interval of planetary motion about the Sun. So when we consider the solar system, only internal forces should be taken into account. And internal forces are the forces of central field. And there are no forces of friction. So these forces are conservative. It means that the energy is not lost. We discussed all these things. And with these assumptions, we understand that we have derived the law of conservation of angular momentum. It means that the vector L is constant in time. It doesn't change. It doesn't change. If you calculate the vector L, we will understand that this vector is perpendicular to the plane where this ellipse belongs. The plane of this ellipse remains constant in time because the perpendicular to this plane coinciding with the direction of this vector is constant in time due to the law of conservation of angular momentum. And also, this law of conservation of angular momentum will give you something more. So this is the definition of angular momentum, and if we want to find the change in time of this quantity, we already discussed it. It's the moment of forces acting on the planet, and the moment of forces acting on the planet is the radius vector product by F. F is directed along the radius connecting the planet and the Sun. So F is directed here. So the only component of force is the radial component. And radial component is parallel to the radius. So the moment, so the torque of forces acting on the planet is 0, and therefore this quantity, a time derivative of angular momentum, is 0. It means that the angular momentum of each planet is constant. So this quantity is constant. The mass of the planet is constant, therefore R times V is constant. R times V well, here it's necessary to consider two components of vector V. One component is perpendicular to, let it be longer, one component is perpendicular to radius, I will denote it as perpendicular component, and another component of vector v is directed along the radius. So here we can put it like this: radius vector product by m, and the velocity is the sum of two vectors, perpendicular vector and vector of velocity v parallel to the radius. A radial component of velocity and tangential component of velocity. Well, tangential, I denoted it earlier as having the index tau. Okay, let it be. Oh no, that's not in this case. That's a perpendicular component. Two components, perpendicular and parallel. Is there any third component of velocity? Z component? No. In this case, no, because the trajectory is flat, and it's two-dimensional trajectory, and so the velocity is also two-dimensional. Has only two components. It has no third component, because the trajectory is not a three-dimensional curve. It's a two-dimensional curve belonging to one and the same plane, like the plane of this blackboard. So if we consider the velocity components, then we can open these round brackets, and we can have, well, mass is constant, and there we have r, vector of r multiplied by perpendicular component plus r multiplied by radial component. Radial component of velocity is parallel to radius, so this term will give us 0. And finally, we will have am r times v perpendicular. What is the angle between two perpendicular vectors? Radius vector and perpendicular component of velocity. These two vectors are perpendicular. It means that angle between them is 90 degrees. 90 degrees, it means that the sine of this sine of this angle will be unit. So when we go to, if we want to consider the magnitude of this vector, the magnitude will be mrv and no sine. Sine is no sine alpha. Sine alpha is unity, because alpha is the right angle here, 90 degrees. So I consider the magnitude of this vector. This is L. And I would like to consider such a vector which is divided by mass. So air times velocity equal to capital L divided by mass. This physical quantity is called angular momentum per unit mass, and I will denote it by small letter L. This is angular momentum of the planet per unit mass of the planet. Different planets have different masses and different angular momenta, but this quantity is also important, angular momentum per unit mass. We will denote it by small l, and it's equal just to r times v. Sorry, we talk about v perpendicular, so here we must use the perpendicular component of the velocity. Perpendicular component, that one. And perpendicular component, I continue this equation, r remains the same, and perpendicular component can be expressed like ds, can be expressed like, let's draw a picture. To make it clear. So here is the elliptical trajectory. Here is the sun of capital M, and here is the planet, and that's its velocity at a given moment of time, and that's the radius vector r at a given moment of time. And in the next moment of time, radius vector will be here, t plus dt. And my purpose is to calculate this area swept by the vector within time interval dt. So in order to do it, I have to find two components of velocity, that is the radial component and the perpendicular component. And perpendicular component if you recall the kinematics of rotational motion, you will understand that perpendicular component equals radius vector phi dot, where phi is the angle, this angle. So this is radius d phi dt, d phi dt. Phi is the angle of rotation of radius vector. So that's relationship taken from the kinematics of rotational motion, which we considered in the beginning of this semester. Kinematics of rotational motion. So phi is the angle at which the radius vector turns, and the perpendicular velocity, the velocity component perpendicular to the radius vector, can be expressed through the vector, using the vector and the angular velocity. That is just the angular velocity omega, if you wish. This is omega. This is angular velocity equal to omega. Certainly it depends on time, and at different points of time, different moments in time, that will be different, as well as radius also is a function of time. So the velocity is radius phi dot, and the velocity component here standing in this formula is radius, so I will obtain radius squared phi dot. What is this quantity r times d phi? Radius vector times small increment in angle. That will be this, by definition of angle, that will be the length of this section. Let's denote it by anything. What other letter is there? S, for example, ds. So radius times d phi is ds, the small section which is shown here, perpendicular to the radius. And therefore the area of dashed figure, the area here, as the area of a small triangle, will be equal to, so this is a small area, dA, it will be equal to radius ds divided by 2. The radius, the area of this small triangle, which is very, very thin, will be its hypotenuse, which is equal to r, times this leg, which is equal to ds, divided by 2, the area of the triangle. So if we divide this equality by dt, we will obtain the increase of the area is equal to r over 2 ds over dt. And this is exactly the perpendicular component. ds dt is the perpendicular component. So looking at this formula, r velocity perpendicular over 2, and looking at this formula, we obtain the following result, that the angular momentum per unit mass, angular momentum L per unit mass, which is equal to radius times perpendicular velocity, radius times perpendicular velocity, which is radius perpendicular velocity, and from this formula we obtain that radius times perpendicular velocity is 2 dA dt, and that is constant in time due to the law of conservation of angular momentum. Angular momentum, capital L, is conserved, as well as the small l, because small l is capital L, constant, divided by the mass of the planet, which is also constant. So angular momentum per unit mass is also constant in time. It's a conserved physical quantity. So law of conservation of angular momentum gives you the result that the rate of change of area swept by the radius vector is constant in time, which means that in equal intervals of time, equal areas are swept by the radius vector. This area swept in 1 hour will be equal to this area swept in 1 hour. And in whatever place of the trajectory you measure this area, you will obtain the same, one and the same quantity. Here the triangle will be very thin, but the area will be the same if this is the same time interval as here. The same time interval, say an hour, taken here for a planet motion, and here. Here the planet displacement during the hour will be small, and here planet's displacement during an hour will be larger, but the area of this triangle and this small triangle will be the same because of the law of conservation of angular momentum, and we have proven it. So, such is the way to explain the second Kepler's law. The second Kepler's law is obtained, can be obtained or derived from the law of conservation of angular momentum. That's it. Apart from law of conservation of angular momentum, there is another law of conservation, which is conservation of energy. And conservation of energy for a planet in solar system can be written as kinetic energy plus potential energy equals some constant, some total energy which remains constant as the planet moves along its trajectory. Kinetic energy is what? Mass of the planet, its velocity squared over 2. Potential energy of the planet in a gravitational field of the sun. We derived this quantity last time, and we obtained that it's equal to minus gamma small m capital M over radius r. So the law of conservation of energy may be written as mv squared over 2 minus gamma small m capital M divided by r equals the total energy of the planet. Total energy consists of kinetic energy and potential energy. That's what is written here. If we divide this equation by small m, we can do it because m is the mass of the planet or mass of a comet or mass of any other object in solar system. What energy? Kinetic and potential. Yes, this is a total energy.
But we didn't take account the internal energy of the planet.
Internal energy? Well, yes, we don't take into account internal energy because it doesn't change. It doesn't change, internal energy. And even if it changes, for example, some celestial body, some comet moves and, for example, its temperature is increased because the sun rays hit this comet. It doesn't considerably change its trajectory. Its motion does not depend on the temperature of the planet, for example. As the planet lives and exists for thousands of years, its temperature may change. It may be cooled. Actually, planets are cooling down gradually, but very slowly. Millions of years, millions of turns around the sun, and the temperature may be diminished by just half a degree. But yes, internal energy is changing, but it does not have any influence on the motion of the planet. So we don't take into account internal energy. Internal energy is not a mechanical energy. And we take into account only mechanical energy here. When do we have to take into account the change in internal energy? When, for example, two planets collide and their kinetic energy will be transferred into internal energy in inelastic collision. Then in this process, yes, certainly we will have to take into account the change in internal energy, but not in this mechanical energy conservation law. Mechanical energy conservation law, mechanical energy here consists only of kinetic energy and potential energy. And we divide this equation by small m, by the mass of the planet. And we obtain v squared over 2 minus gamma capital M divided by R equal to capital E divided by M. What is this? This is the total energy of the planet referred to the unit mass of the planet. If we divide the total energy by the mass, we obtain the mass, the energy of the unit mass. And we will denote this quantity by epsilon. So that's just the law of conservation of energy, and epsilon is the total energy per unit mass. The total energy of the planet per unit mass of this planet. Again, we consider V, as in the previous example, we consider vector V as consisting of two components, the radial velocity plus perpendicular velocity. And perpendicular velocity from this equation can be expressed as, so we have radial velocity plus perpendicular velocity. Perpendicular velocity can be expressed as L divided by R. L is the angular momentum per unit mass divided by radius vector. This is a scalar quantity, so in order to be consistent in writing a vector quantity, I have to add some vector, for example, some vector directed along the radius, as this is a perpendicular velocity, this is a unit vector perpendicular to the radius. It doesn't have much physical sense here because vector equation, vector quantities will be finally turned into scalar quantity after I find the square of this velocity. So when I find the square of this velocity, that will be what? V squared is the scalar product of V times V, and that will be scalar product of radial component of velocity plus L squared over R squared L squared over R squared, and plus the plus the scalar product of radial component and perpendicular component. But when you find a scalar product of two perpendicular vectors, the cosine of that, what will be the cosine of 90 degrees? That will be 0. So I will just indicate here 0, which is the scalar product of two perpendicular vectors. When I find the when I take the v squared, I will have to find the square of the first terms plus square of the second term plus double product of these two terms, which will be 0, because these two vectors are perpendicular to each other. So v squared will be taken from here and substituted into this equation, and I will find that this is a v radial component squared over 2 plus L squared divided by the same 2r squared minus gamma capital M divided by r equal to epsilon. So this is an interesting equation, which is the consequence of the law of conservation of energy, nothing more. And also the law of conservation of angular momentum was used here. So this is a combination of conservation of energy with the conservation of angular momentum taken into account in this term. And this equation includes the function, some function of radius, this one, and another term is also a function of radius, that is the distance from the sun to the planet. And this term is also a function of the radius because the velocity will be a function of radius. And all this is constant because this epsilon is constant due to the law of conservation of energy. This is a constant. So from this equation, I can find the velocity as a function of distance to the star. The velocity of the planet as a function of distance to the sun. So this term is, I remind you, is the kinetic energy per unit mass. Why per unit mass? Because I have divided all this equation by mass. So this is the kinetic energy of the planet per unit mass. And the second term is called, as L is the angular momentum per unit mass, angular momentum of the planet. So this term is called some sort of energy related to rotation, but this energy is related to, this term is related to the rotation of the body, and this term is called a, so what's the proper word? Forgotten it. It slipped my mind. Centrifugal energy. This is the centrifugal energy. And these two terms together are called the effective potential energy per unit mass. Effective potential energy per unit mass, which is a function of radius, of distance to the planet. An effective potential energy. So the equation can be written as the velocity squared, the radial component of velocity squared over 2 plus the effective potential energy as a function of distance r equal some constant quantity, which is the energy of the planet, total energy per unit mass. Well, it's not difficult to draw a graph, to draw this function effective energy as a function of radius. The effective energy is equal to L squared over 2R squared minus gamma capital M divided by R. So if I draw the graph of this function, and here will be, along the horizontal axis, will be the distance from the sun to the planet, shown here along the horizontal axis. And along vertical axis, I show this effective energy, which is defined, by definition, is equal to this expression. Then it's easy to draw the graph of this function. What if R is increased? What will happen? If R is increased, then each term will dwindle to 0. Each term will diminish and tend to 0. But when you have R in denominator, that will diminish slowly. And when you have R squared in denominator, that will diminish quicker. So this term will tend to 0 quicker. Because if you diminish distance by 1,000 times, this term will become 1,000 times less. But the first term will become 1 million times less. So the first term will vanish and will turn to 0 much, much quicker than the second term. So if we have large distances, then the second term will be prevailing here in this formula. It will be the main term. And so we know the behavior at large distances. It will be determined by the second term. The energy will be minus, will be negative, and it will be growing slowly as in magnitude, growing in absolute magnitude as the radius decreases. And it will become smaller and smaller as the radius increases. So that will be the behavior of this function at large distances r. What happens at low distance, at small distances? At small distances, the first term will be larger. Both terms will tend to infinity at small distances when r goes to infinity. If distance goes to infinity, if distance goes to 0, if r tends to 0, the second term will tend to infinity, and the first term will tend to infinity. But the first term will tend to infinity much, much faster. Because if you diminish distance r, for example, by 1,000 times, the first term will increase 1 million times, while the second term will increase just 1,000 times. So at small r, the first term is prevalent. It will be much, much larger than the second term. And so the first term gives you, it's positive, and the energy will be positive, but it will be sharply dependent on r, something like that. And somewhere at some certain r, the first term will be equal to the second term. That means that at this particular point, this combination will be 0. So that's the 0 when the effective energy is 0. When the second term equals the first term, then that will give you 0 at some point. And here it's obvious that the function will go something like that. And from here, we obtain that the velocity squared, radial component of velocity over 2, equals epsilon minus u. And note that any quantity squared is always positive. Whatever velocity you take, velocity squared is always positive. So this expression should be always positive. Only positive values of this quantity will mean that the velocity is real. That is, only for positive quantity the velocity is real and positive, it's not imaginary, and it corresponds to a real motion of particle, real motion of planet. So if you have epsilon like a some negative quantity, if this epsilon some negative quantity, minus, I would put it like minus epsilon modulus. So as to indicate that this is negative, then what does it mean? Where the velocity will be positive, where this difference will be positive between negative epsilon and this function of effective energy, effective potential energy. Only within this interval of radii, the minimum possible distance from the planet will be r1, and the maximum possible distance of the planet from the sun will be r2, and the planet will go in such a way that the distance from the sun will change between r1 and r2, so that the planet will somehow go here in this section, and the planet, it will be impossible for the planet to go closer to the sun, because here the velocity squared will be negative, which is impossible for the planet. Here, the velocity, if distance is smaller than r1, the velocity squared will turn to be negative. It's impossible. So this section, this area will be forbidden for the planet. It will be forbidden. Also, this section will be forbidden. The distance larger than r2 will be impossible. The planet will move in elliptical trajectory so that the distance from the planet to the sun will change within this section. If on the other side this quantity is positive, larger than 0, then any distance is possible larger than this one, larger than this minimum distance. Any distance is possible. So only these distances will be forbidden, all other distances will be possible. So that this planet, such a celestial body, will move to the infinity, And another situation when epsilon is 0, then the planet could move, or any celestial body could move from this minimum radius to infinity. So there are 3 possible situations. First, when epsilon is larger than 0, the trajectory of the celestial body will be a hyperbola. I give you that without proof, but just indicating that in this case the celestial body can move to infinity, and the trajectory will be hyperbolic. If epsilon is 0, that is total energy of the planet per its unit mass, then the trajectory will be a parabola. And if epsilon is less than 0, then the trajectory will be elliptical. The planet moves along an ellipse if its total energy is negative. If total energy of some celestial body like a comet is 0, then it will move along a parabolic trajectory. It will start from infinite distance to the sun, then go closer to the sun from infinite distance, then will go closer to the sun up to this point, and then go again to the infinity along the parabolic trajectory. And then if the energy is higher, larger than 0, then the trajectory will be hyperbolic. So we can draw it in this way. This is the elliptical trajectory of a planet whose energy is less than 0, and if the energy is about 0, then the trajectory will be a parabolic trajectory. That is epsilon less than 0, that is epsilon equal to 0, and if epsilon is larger than 0, then the trajectory will be hyperbolic. The last two possibilities, hyperbolic trajectory and parabolic trajectory, mean that the planet will go to infinity. Such motion is called infinite motion. And when the total energy is less than zero, then the planet goes in between two distances from the sun, and such a motion is finite motion. It's finite motion. Such planet cannot go to infinity. It will remain within finite limits. So that's what I wanted to tell you about the finite and infinite motion. Oh, that's the end of our class. So let's finish it.